Hello and welcome to section 14.7 on change of variables in multiple integrals. This is the multivariable analog of substitution for single variable integrals that you see in Calc 2. And so to remind you of a few things related to substitution, as well as to highlight some of the underlying geometry behind substitution, that's going to really help us when tackling multiple integrals, we're going to look at this first question on the worksheet. And this says to consider the integral from 0 to 3, the square root of 4 plus 2x. If we make the substitution u equals 4 plus 2x, then du is equal to 2 dx, and this original integral can now be seen to equal this integral from 4 to 10 of the square root of u times 1/2 du. Our job is to sketch pictures of the areas that these integrals compute, and to give a geometric explanation as to why these areas are equal by appealing to the transformation u equals 4 plus 2x. All right, so in Calc 2, you'd really just focus on the computational side of this question. So you have some integral you want to compute, and you're thinking, well, what's the substitution I could make that will give rise to a more computationally friendly integral? And here, by setting u equal to 4 plus 2x, you're trading in the job of having to integrate the square root of 4 plus 2x with the job of having to integrate 1/2 of the square root of u. Okay, so you simplified things. Okay, so what we're going to focus on next is what this equality of integrals says about area. So here's a picture of the integrand for the integral off to the left. Here's a picture of the integrand for the integral off to the right. And the fact that those two integrals are equal says that these two areas then are in turn the same. Okay, and our job is to explain why geometrically. Okay, so first note that this interval from 0 to 3 has length 3, and this interval from 4 to 10 has length 6. Okay, so there has been a horizontal stretch by a factor of 2. Okay, the other thing to note here is that there's a 1/2 in front of this square root of u, and so there in turn has been a vertical compression by a factor of 2, okay, by making this transformation. And I've included these labels here on the vertical axes to really just highlight that, right? The range of this blue curve is from 2 to the square root of 10, whereas for the purple curve, it's from 1 to root 10 over 2. So it seems totally plausible that combining a vertical compression by a factor of 2 and a horizontal stretch by a factor of 2 would preserve area. Okay, so we're going to unpack that now in a little more detail on the differential level by considering what effect this transformation, u equals 4 plus 2x, has on the number line. So we'll start by just looking at what effect doubling a number on the number line has. And that, of course, is going to just stretch the the interval here by a factor of 2. Okay, so you could think about stretching a rubber band that's pinned at x equals 0 by a factor of 2. So 1 will get stretched to 2, 2 to 4, 3 to 6, so on and so forth, and it would fix 0. Okay, so now if we add 4, that's just going to take those stretched points and shift them right 4 units, right? So 0 would get shifted to 4, 2 gets shifted to 6, 4 to 8, and 6 to 10. Okay, and as a consequence of applying this dilation and shift, if I look at a little length here on the x-axis, I'll call that length dx. Okay, that is going to get stretched to a length of 2 dx. Okay, so for this length du, okay, right, if this thing is the image of this length up here, okay, then du will be twice this original length. And really that relationship of du equals 2 dx, it really is due to the dilation, okay? The shift won't actually affect lengths on the interval, but the dilation does, okay? And so that really is what this differential computation that we made up here, that's what that really says about the effect on the number line that this transformation u has. Okay, so now what does all of this say about area? Well, let's say I have a little differential strip of area under the purple curve, and its width is du and its height is the height on the purple curve, so that's just 1/2 times the square root of u. Okay, so now if I consider this corresponding strip over here under this transformation, okay, it has width dx and height of the square root of 4 plus 2x, right, just the height on the blue curve. And so now looking at the area of this strip, which is just the product of the root of 4 plus 2x and dx, well, the fact that we're replacing 4 plus 2x with u, and through this relationship with lengths on the x-axis and lengths on the u-axis, okay, dx would be half of du. Moving that 1/2 in front, I see that this area here off to the left is equal to this corresponding area over here. Okay, so in terms of these integrals, okay, what do these integrals do? Well, they just add up these differential strips to fill out these areas. Okay, so for each differential strip I stack off to the left, there's a corresponding differential strip over here whose area is the same. And so their sum would be the same. And that's a way to see this equality of integrals, okay? So what we're going to do in the next video, kind of taking our first steps towards substitution with multiple integrals, is we're going to look at transformations not of the number line like this transformation is doing. We're going to look at transformations of regions in the xy plane. Okay, so I will see you there. Thanks so much.